Pleased to be here today. My name is Andy Hock. I'm the Vice President of Product at Cerebras Systems, where we are building the next generation of compute for deep learning. Very pleased to be here today with my colleague and co-host, Professor Mark Parsons. Mark is the EPCC Director and Associate Dean for E-Research at the University of Edinburgh. Today, we're going to talk to you about large-scale AI for data-driven innovation, particularly around an exciting new deployment, access, and hosted service opportunities associated with a new CS1 Cerebras AI computer system at EPCC and the Edinburgh International Data Facility. This leading-edge AI deployment will enable the next wave of natural language processing and data science research for public, private, and academic sectors across the city region and in the UK. So with that short introduction, Mark, I will share my screen and we'll kick off the webinar. Thanks once again. We're really looking forward to the discussion.
Thanks very much, Andy, for a great introduction. I'll try and live up to it. So hello, everybody, and thanks very much for joining. We've got a good number of people on the call. So I'm going to talk a little bit about why we've chosen to invest in this Cerebras system, a little bit about the Edinburgh International Data Facility, and a little bit about our first projects. And then Andy's going to spend some time talking about the detail of the Cerebras system and some of the amazing technology behind it. Next slide, Andy. So I know some of you on the call will know what EPCC is, but some don't. So just to introduce my organization, EPCC was set up, in fact, in 1990. Used to be called Edinburgh Parallel Computing Centre, but we prefer EPCC. We've got 115 staff, still growing. We're the UK's national service provider for many of the largest supercomputers in the UK, including Archer 2. But we don't just do supercomputing and traditional modeling and simulation. Over the last 5 or 6 years, in fact, we've massively grown our data science activities and our work with AI. And in particular, we've created this new facility in Edinburgh, in the Edinburgh City region, called the Edinburgh International Data Facility. And it's that funding for that facility and what we're creating inside it that has brought us to purchase the Cerebras CS1. Next slide, Andy. So the data-driven innovation program is really, really important for our region. It's capitalizing on the academic excellence at Edinburgh in data-driven innovation, but not just the academic excellence. There's a huge number of companies in the Edinburgh City region that are developing new products and services, making and then selling them globally. And we want to capitalize that, support those companies and grow new ones and attract new investment into the city region. And we've got this tagline that they want to be the data capital of Europe. And we picked that because largely nobody else had picked it. It does describe what we're trying to be. We're not just about academia, we're not just about commercial usage. We also think that there's an enormous amount of value to be gained in the public and the third sectors. If you look at a typical European economy, about 50% of the economy, in fact, is public sector. And if you don't innovate in the public sector, you can't improve the lives of the people in your region. So we really believe strongly that there are huge opportunities there as well. We want to unlock large economic opportunities. We're also going to train 100,000 people in data technologies. That's about 1/6 of the entire population of Edinburgh. And to do that, we need an underpinning infrastructure. And that infrastructure is the Edinburgh International Data Facility. And we've created 2 key partnerships to deliver the IDF. One is with HPE, who have the main IT contract for the data science cloud we're creating. But as part of that, we've partnered with Cerebras for the large-scale AI that we want to deliver. Next slide, please. So This is a rather complicated picture, but what I want to get across from it, if you look at the purple area, you'll see a series of buildings, and these are the centres that have been created as part of the City Deal programme. EPCC is based in the Bays Centre, which is a focus on digital technologies and space and satellite. But for example, we've got Easter Bush, which is focused on agritech, the Usher Institute that's focused on health, Edinburgh Futures focused on fintech, tourism festivals, all of these things that the Edinburgh City region does well. And of course, the National Robotarium that's actually hosted at Heriot Watt University. And at the centre of all these activities is the Edinburgh International Data Facility that will focus on supporting all of the training we do, all of the people in the centres we create, and all the projects that we undertake in the local area and with international partners. Next slide, please, Andy. So over the past 18 months or so, a little bit longer, 2 years really, we've been gradually building the facility itself. One thing that we've tried to do from the start is to build on the existing and traditional HPC infrastructure that we have. So these are Archer 2, Dirac, Cirrus, etc. These are large HPC systems. Archer 2's a 25 petaflop traditional supercomputer, for example. But what we want to do is also have a large data facility focused on data science cloud services. And there's really two parts to that. One part is traditional data science cloud, the VM servers, GPU servers, etc., etc. The other side is a data safe haven facility. So we operate a number of data safe havens, such as the Scottish Government's National Data Safe Haven for Health Data. And that's one aspect of this. However, in the data science cloud area, next click, please, Andy, we've put this Cerebras CS1, and this is to allow us to do some really, really large AI training projects and other projects. And one of the things I want to talk about is why we think we need that when we've also got large scale HPC. Next slide. So there's a real conundrum today in the computing world between supercomputing and data science. And I think all of us understand now this is not an easy to solve problem. So on the one side, you've got large scale supercomputers that really haven't changed enormously in the last 20 years. They're largely batch system based with Slurm or whatever. They tend to be bare metal, so there's no virtualization on top of them. And they're very much focused on numerical performance with limited memory per core. They tend to have limited internet connectivity from the back end. So they may have a very fast internal network, but going out to the outside world is not one of their fortes. And they're typically a Linux-based operating system like Red Hat, Enterprise Linux, or CentOS. They also tend to have a non-standard network, but they are connected to high-performance parallel storage for bringing data in and out of the system. But then compare that with the data science system, where it's often virtualized using OpenStack. Kubernetes environments are widely used to deploy containerized software. There's a lot of focus on distributed object storage. So you're not really looking at POSIX file systems. You're looking at accessing your storage through an S3 interface, for example. There's a range of memory requirements. And one thing we do see is people get to the point where they're pushing their virtual machine too far and it can't deliver enough horsepower. It's a key part. But they live in this much richer internet-enabled environment where you can bring down applications from the internet, you can interact with software repositories, etc., etc. And the operating system is typically Ubuntu, etc., and more desktop Linux type operating systems. Next click, please. So the problem on one side is that the supercomputer system over-constrains the software that can be run in it. Next click. But the data science side of things often runs out of horsepower for demanding users. And this is really what we're trying to solve with our investment in the CS1. Next slide, please. So as Andy said, we took the decision towards the end of last year to invest in a Cerebras CS1. That arrived in March 2021. We really pushed Cerebras to deliver quickly, and they did. It's quite a phenomenal piece of hardware, and Andy will talk in more detail about it, but it's basically this beautiful 21 centimeter by 21 centimeter piece of silicon, wafer scale integration with 400,000 small AI cores on it, really that look very much like a sort of data flow engine. It's got on-chip very fast memory and lots of it, and its internal memory, its internal interconnect runs at the hundreds of petabits level. Externally, it's connected over a series of Ethernet connections. I'll show them in the next slide. And what Andy's going to talk about in more detail is that it's got a very AI-focused software stack. It's designed to be easy to use by people who are used to things like TensorFlow already. And it's hosted inside our facility by Hewlett-Packard Superdome Flex. And we've made a conscious decision to do it like that because we find the Superdome Flex is an excellent stepping stone between this world of the supercomputing massively parallel system and the virtualized data science VM world, which can run out of grunt at sometimes. Next slide, please. So this is the setup that we've put in place with the CS1. It's not dissimilar to the setup that Pittsburgh Supercomputing Center went with in the US. On the right-hand side here, we've got our new HP cluster store system, 20 petabytes of storage, which is plugged into our data center network. That communicates with the Superdome Flex, which is an 18 terabyte main memory system with 100 terabytes of NVMe storage specifically bought for the Cerebras system. Interestingly, though, in our most recent projects, we've actually found that the cluster store with a very fast network we've put in is doing really well at providing data at a rate that works with the Cerebras very well. Now, the Cerebras itself is connected through a 100 gigabit Ethernet switch with 12 Ethernet connections. So we were very impressed by this. This is the first time we've breached the terabit networking regime. So that's 1.2 terabits of network connectivity onto the Superdome Flex. And on the left, we've got the Cerebras system with its 400,000 cores. Next slide, please, Andy. So here's a very embarrassing picture that Andy slipped in of me beside the Cerebras system, but it's just to prove that we've got it, that it's running. The red lights on the front show that it's running. There I am looking very proud of it inside our new computer room at our data center. It went live in early May. We had some training sessions and we've started a whole series of projects already. So the first experiments we're doing around NLP are using BERT models and TensorFlow, and we expect that to be a particularly important area for us going forward. It's a big NLP group at Edinburgh University, and I think they're going to do some really exciting things with the system. But it's not just about our informatics colleagues. Actually, we want the system to be used across the university. So one of the early projects we're doing is a text data mining project in the social sciences. One of my teams looking at the GCN, LSTM, Conv1D networks that come with the software framework we have on the CS1. We've got a set of PhD students who are part of the biomedical AI PhD program. They're basically taking the projects that they've been running to date on GPUs and putting them onto the Cerebras system. And then we've got two commercial projects that have already started. One's with a local cybersecurity company and the other one's with a local robotics company. There's also some of my colleagues in a collaboration between EPCC and informatics that are looking at programming models for the system. And I think all of these things are really, really exciting. We've also got another group that I haven't put on this slide who are looking at genome-wide association studies work as well on the system. So it's really actually, given that we've only been running for just over a month, I'm really pleased with the projects that are coming onto it. Next slide, please. So this is the final slide before I hand over to Andy. There are a variety of different ways, and we'll talk about this more at the end of the project as well, at the end of the webinar as well, about how you can access the system. So it's very easy to access if you're involved in a data-driven innovation project as part of the City Region program. You just fill in, we'll get in touch with us or fill in the form at the end that Andy will talk about. The system is also paid for partly by the Excalibur Hardware Enabling Software Program, which is the UK Exascale program. And 15% of the system is accessible to UK Excalibur users, I think there are one or two of those users on the webinar today, and we'll very soon be opening up an applications process for that. For industry and commerce, we're very keen, and this is something that EPCC does in all of its supercomputing systems. We encourage industry access, and we're very well known for it in Europe. So we're very keen to welcome companies onto the system. You can get free exploratory access if you want to take one of the models you're already working on and see whether it'll compile, see how it would fit into the Cerebras programming model. Very happy to give you free exploratory access. And then if you want to use it for production, we would do that on a pay-per-use basis thereafter. We have online training, which is already available. That will certainly grow over the next few months. And then system supports provided by the normal EPC help desk, who then pass on queries to Cerebras where we can't easily solve them ourselves. I think that's me. Thank you very much, Andy.
Brilliant. Thanks, Mark. It's a great introduction to the system and the deployment at EPCC and EIDF. I have to be honest, it's hard for me to throttle back my excitement about this. You're absolutely right. The early projects that we're seeing come to life on this system are incredible. And we're really looking forward to expanding our partnership and work with more members of the public and private research community through the system. So I'll say a little bit about Cerebras Systems, the company, also introduce our technology and give you an idea of the programming model and performance of this system so that you have some insight into how this system might be applicable to your work for the audience in the webinar today. Cerebras as a company, we are an AI computer systems company. We were founded in 2016. Our founding team has decades of experience in chip design, system engineering, and bringing high performance computing solutions into data centers across the world. But we built the team and the company at Cerebras not just to make an incremental improvement on an existing processor technology to get a little bit more performance out of a legacy architecture. Instead, we saw an incredible opportunity to build the right processing engine for what we see as one of the most important computing workloads of a generation in training and inference for neural networks in deep learning and artificial intelligence. We saw an opportunity to transform the compute landscape by building the right computer system to radically accelerate artificial intelligence work, not by a little bit, but by a lot. And with that experienced team and big vision, we've been fortunate over the past several years to secure some smart and strategic investment. And we've grown the team now to over 300 world-class engineers across hardware from chip design to system, software from microcode and compilers all the way up to ML frameworks like TensorFlow and PyTorch, where data scientists and ML researchers operate every day. And we also have an ML research team that works with our partners using our systems to help develop new neural network architectures, new ML methods, and new algorithms that can uniquely take advantage of our hardware architecture. So our basis and our thesis for the company is relatively straightforward. We observe that whether it's natural language processing or biomedical research or research into autonomy or industrial applications in web and social media or robotics, that AI has transformative potential to change the way that we process data and make decisions. But it is fundamentally constrained by computing infrastructure today. The primary symptom of that constraint is that state-of-the-art deep learning models simply take too long to train. It's not uncommon for large models in the natural language space, such as BERT, for example, to take days or weeks of computing time, even on large clusters of graphics processors on real-world data sets. And one training run constitutes maybe one experiment in the life cycle of a research and development project. So days or weeks is simply too long. And the reason for that long compute time is fundamentally that existing machines were not built for this work. Devices such as CPU and GPU are suitable, but they're not optimal for this work. At scale, they can be underutilized and inefficient and difficult to program at cluster scale, particularly in the data science and ML research world. So we saw this as an opportunity to create a new compute solution to accelerate this work and take those days or weeks of compute time down to minutes or hours and increase the iterative nature and ability for researchers to bring new applications to life more quickly in AI so that we can together realize the potential of that for our work. What is really needed, though, is truly cluster scale compute resources for sparse linear algebra operations that are the foundation for all neural networks and indeed some HPC workloads in the context of high memory bandwidth and high communication bandwidth. And to realize that vision, we built the Wafer Scale Engine, the processor shown here that Mark introduced earlier. The Cerebras Wafer Scale Engine is the largest processor ever built. It is 56 times larger than the largest chip built previously. It's 46,000 square millimeters, so 21 centimeters by 21 centimeters of unbroken silicon with 1.2 trillion transistors, 400,000 individually programmable cores. These cores, as Mark mentioned, are fully programmable. They have a general purpose instruction set. They also have a set of extensions to that instruction set that enable efficient, high-performance processing of tensor-based sparse linear algebra operations. So these are cores that are built for the work of deep learning. In addition to those cores, we also have 18 gigabytes of all on-chip SRAM that allows us to hold your entire deep learning model in state and access the weights and parameters of those models in a single clock cycle, all on silicon. And then in addition to holding the entire model, we also need to drive data across this device from core to core and processor to processor. And for that, we have an on-chip network. Each one of those 400,000 cores is directly connected to its 4 nearest neighbors over silicon in a high bandwidth, low latency interconnect mesh. And the entire data flow traffic pattern from core to core and across the entire wafer is fully configurable in software. Once we arrived, though, on this novel wafer scale architecture for the processing engine of our system, we had to completely rethink packaging, power, cooling, and delivery of data to this device. We couldn't simply take that wafer and deploy it into a standard desktop machine or 1U standard rack mount server in the data center. So at Cerebras, we had to take a full systems level view of the right solution for AI compute. And our system engineering team then designed and built the server shown here, which we call the Cerebras CS1. Mark may have been embarrassed by the photograph, but Mark, you're a very effective scale bar for this device. This single server is powered by a single one of those wafer scale processors. It stands at 15 standard rack units tall, about 26 inches tall. So it takes about 1/3 of a standard data center rack. We take 23 kilowatts of power through standard power connections, and we connect to adjacent infrastructure, such as the Superdome Flex in the EIDF deployment, over 12 standard 100 gigabit Ethernet connections. So standard connections all around, so the system is built to be easy to deploy and operate and maintain from a data center standpoint. But of course, because the Wafer Scale Engine processes data so quickly, we had to provision 12 of those standard 100 gigabit Ethernet connections for an aggregate system level IO of 1.2 terabits per second. Depending on the workload, this single device delivers the compute performance of many tens to, in some cases, hundreds of traditional GPU machines. So in this single system, from a data center standpoint, you can imagine replacing racks of legacy general purpose machines and unlocking true cluster scale deep learning performance, but all within the system of one device and a fraction of a single rack. So then for my data science and research colleagues on the call, you might be asking, how do I program this machine? For that, Cerebras has built our software platform that connects users programming in standard ML frameworks, such as TensorFlow and PyTorch, directly to our machine, the CS1 and the Wafer Scale Engine. So the short answer is you program the machine using standard ML frameworks. We've invested significantly in our software stack to make that easy. In summary, you log into a host node, such as the Superdome Flex, where our software lives alongside your ML framework in a standard software container. You describe your training or inference program in the standard semantics of your ML framework. And at runtime, our software extracts and translates your compute graph into an intermediate representation that we call LAIR here. This intermediate representation is effectively the top of our software stack, and it describes the compute operations at each and every layer of your neural network and the communication pattern between those layers. Our software then automatically matches a high-performance kernel to each and every one of those compute ops. So we have a software library of kernels, which are effectively high-performance microcode programs for common deep learning operations. For attention-based natural language models, such as BERT, for example, we have attention and fully connected. For some of the other models that Mark mentioned, for example, we have 1D convolution, LSTM for recurrent neural networks, and kernels for a host of graph-based neural networks like GCNs. So we have a library of high-performance kernels, one of which is mapped to each and every layer of the user's neural network. And then our compiler automatically places or allocates compute and memory resources on our wafer for each and every layer of your neural network. So effectively what we've done in these steps is we've converted your N-layer neural network into an N-stage data flow pipeline to run at high performance and high efficiency on our device. Input data is then streamed in from external servers over our 1.2 terabit per second interconnect, in this case from the Superdome Flex onto the device. And then weights are available for export or subsequent use on our machine. So this entire stack is programmable with today's ML frameworks. We're operating primarily through TensorFlow today. We will be releasing support for PyTorch in September. And for those of you working in PyTorch today, it's also fairly straightforward for teams or researchers to move their code from PyTorch into TensorFlow if you want to get started immediately. We have a library that is growing for high performance deep learning ops to give us coverage over a broader and broader set of neural network architectures and application types. And the entire stack then is also customizable and extensible for other applications. We're building a set of lower level programming tools for custom kernel development for both deep learning and non-deep learning applications, and a host of programming tools and lower level APIs so that you can write your own kernels and call them and run them on the device, both for deep learning and HPC applications. One big advantage of this software platform in the context of our system is that it gives researchers access to a cluster scale AI compute resource, but with the programming simplicity of a single node. So the value here of performance is really for research and development in the reduction of training time from days or weeks to minutes or hours, allowing researchers to test and learn from many more ideas per unit time. Or equivalently, bring much, much larger data sets to your model so that the trained model better represents the real world phenomena that you're trying to capture. At inference time for models in production, our machine can support high throughput inference for full scale models at low latency and achieve full utilization down to batch size 1, giving you greater performance and flexibility at production time for models in inference. Last but not least, as I also come from a research background, I think we built this machine not just to accelerate the neural network architectures of today, but really to serve as a platform for researchers to develop new neural network architectures, new ML methods and algorithms that may not be efficient or practical or even possible on existing machines. I'll give a couple of use case examples. The first one here is training BERT for a web natural language processing application. We compared training time of the same model on the same data set on the CS1 compared to a NVIDIA DGX A100 machine. The DGX A100 uses 8 A100 GPUs. What you see on the left is a chart that shows the evaluation accuracy over time for training of the DGX A100 in blue and the CS1 in orange. On the right, you can see the accuracy achieved as a function of time, as well as the acceleration factor delivered by the CS1 for this work. We set a bound of 2 weeks for this experiment to go through hyperparameter searches and identify the right set of hyperparameters for the model to converge. And the customer in this case set an accuracy threshold of 98%. This is the accuracy to which the model needed to be trained in order to be qualified for production use in their Web NLP application. Interestingly, over the course of a 2-week period, the CS1 machine achieved that 98% target accuracy in just under 45 hours. Using the DGX A100 machine, hyperparameter search and tuning took quite a bit of time, and over the 2-week period of the experiment, they were not able to achieve 98%. But looking at the next closest accuracy achieved by both machines, 97.3, what we can see is that the DGX system took just over 218 hours to train to 97.3% accuracy. Our machine, the CS1, just over 23 hours. This is a 9.5x acceleration factor in time to accuracy over that 8-way GPU server. But in truth, because wall clock compute does not scale linearly across multiple GPU machines, you can think here that the CS1 is actually far greater than 9.5 DGX compute equivalents in terms of delivering wall clock training time, excuse me. So this solution delivers the wall clock compute, if we look at BERT scaling across DGX machines, of far more than 10 or even 20 DGX machines, greater than a cluster of DGX systems. In another collaboration, looking once again at large BERT model training, which is an area of extraordinary interest in the research community today, we looked at training various BERT models across the PubMed biomedical literature database with an industry partner in pharmaceutical and biotechnology research. And what we found was that in this case, not only did our system deliver greater wall clock training time, but it was also faster time to solution and iteration because of that easier programming model. Right? In the case of programming a GPU cluster, the research team and our partners had to do extensive hyperparameter tuning. They had to use additional programming tools such as Horovod and OpenMPI to orchestrate communication and machines across their cluster. All of that takes time. And so in this case, our customer compared end-to-end time to solution from a research concept to a model in production, comparing that overall time to solution in their GPU cluster compared to the CS1. What they discovered was that faster iteration time allowed them to go from research concept to model in production in 4 weeks on our CS1 machine, compared to over 4 months on their GPU cluster. So this easier programming allows for more quick, more iterative exploration of the model space to more quickly arrive on a model in production. And last but not least, I wanted to say that the CS1 and the Wafer Scale Engine is really just the beginning of our technology roadmap at Cerebras Systems. We've recently announced our 2nd generation Wafer Scale Engine and CS2 system. Compared here to the specifications of the 1st generation Wafer Scale Engine, our 2nd generation processor is fabricated at the 7 nanometer node. It maintains that same 21 by 21 centimeter form factor for the wafer, but we have now 2.6 trillion transistors, and instead of 400,000 cores, the WSE2 has 850,000 cores and goes from 18 gigabytes of on-chip memory to 40 gigabytes of on-chip memory. So this new wafer gives us more than 2x the compute performance and memory capacity to deliver even faster wall clock training and inference time and support models of much, much larger scale. The WSE2 will be deployed in an upgraded system chassis that we call the CS2. That device has the same form factor and same connections to the network. So a CS1 can be upgraded with a CS2 directly and deployed to deliver even greater performance and scale to our users. So we're really excited about this next step in our technology roadmap to delivering greater performance and scale for deep learning. So I'd like to close here. Thank you all for participating in the webinar. We're tremendously excited about the deployment at EIDF, the early interest in applications and research projects across the academic and private sector community. The system at EIDF is running today and allows researchers to explore more ideas in less time and reduce the cost of curiosity. As Mark mentioned, the system is available for test and remote access for the community of researchers in the EIDF sphere and also for Excalibur participants. The link below where it says apply here is a link to a form that you can fill out if you're interested in testing or early access for your applications. These slides will be shared with participants after the fact of this webinar so that you can click there and follow that link and let us know about your interest and get time on the system. Applications will be reviewed by Mark and the EPCC team as well as Cerebras, and we'll get back to you just as soon as we can. We're really excited to host even more projects and applications on this machine and can't wait to get started with you. So thank you.